In the last two lectures, we have discussed various techniques for medium access control. We shall continue our discussion on medium access control techniques in this lecture. In the last two lectures, we have seen in absence of standard, various vendors and also how various contention based techniques can be used. And these two approaches, the round robin and contention based approaches, are suitable for local area networks. Later on, when we shall discuss various standards for local area networks, we shall see how these medium access control techniques are used there. Now, today we shall consider another multi-access media that is not local area network, that is used in satellite-based wide area networks. There also there is a multi-access medium which has to be shared, and so we have to use some medium access control techniques. So I am taking this opportunity to discuss the medium access control techniques which are used in satellite-based wide area networks. Let us look at the scenario of satellite-based networks. We have a satellite in the sky, or a repeater in the sky, you can say. These are the solar panels which provides power to the satellites. And the main equipments are here. Now it has got several transponders. So this is one transponder, disc-like antenna, as you have seen. So these are the transponders. So each satellite is provided with a number of transponders. The number is usually about 12. So there can be 12 transponders which are used for communication purposes, and each transponder can receive packets from ground station and can send packets towards ground. This is, as you know, the uplink, using uplink frequency, and this is using downlink frequency. And here is Earth. Now, a transponder can cover, each transponder can cover an area of say 10,000 kilometers across on the surface of the Earth. So this transponder will cover this much area, and this transponder will cover this much area, and so on. And there are two ways of doing it. 10 kilometers across can be covered using what is known as wide beam. And by using spot beam, the area that can be covered is about 250 kilometers across. Now, the transponders can be focused on different areas for certain duration for communication purpose, and that duration is known as dwell time. Now, in this scenario, the ground stations in this area, which is about 10,000 kilometers across or 250 kilometers across, you can have a number of ground stations, VSAT stations on the ground. Now, as you can see, there is a single uplink frequency which are being shared by all the ground stations covered under a transponder. However, this downlink frequency can be used for broadcast purposes. That means whatever signal is transmitted is being received by all the stations in that area which is covered by a transponder. Essentially, the transponder is acting as some kind of bent pipe. Using uplink frequency, a station is sending signal, the satellite is receiving that signal, so it will accept uplink signal. Second thing is it will translate that uplink signal to downlink signal. Then it will transmit downlink signal. So translation will take place and it will then send it towards the ground stations. So it will transmit downlink signals. So this is how a satellite communicates, and as you can see here, the uplink signal that is being shared by all the stations, and for that purpose we have to devise medium access control techniques. Let us see the key features or characteristics of the communication for wide area networks through satellite. First of all, there is a long delay. As you know, the satellite is located at about 36,000 kilometers above the sky on a geostationary orbit, and the round trip delay is about 270 milliseconds. That is a round trip delay. That means whenever the signal which is being received by the ground station, that was transmitted by one of the ground station about 270 millimeter ago, before 270 millimeter it was sent earlier. So 270 millisecond earlier a signal was sent, and that is being received now. So that is the situation in case of satellite based communication. Another is, in this case, the bit length that is the entire duration. That means, say, from here to here, throughout the path, if you send signals, what is the length of that? That will depend on what rate you are sending. Suppose you are sending at the rate of 64 kilobits per second. Since the round trip delay 64, since the round trip delay is about 1/4 of a second, the bit rate will be about 1/4 of this approximately. So this will be cover about 16,000 bits. That will be the bit length. Now if you are sending at a higher speed, say 50 megabits per second, then it will have about 20.5 million bits. That is the bit length, that is the number of bits simultaneously present on the path. Now in this case, the advantage is all the stations receives its own signal. So we find that there are three important characteristics. First of all, there is a long delay, which is disadvantageous, and it takes about 1/4 of a second for the round trip travel for the signal from the ground station and back to the ground station. Then the bit length, the number of bits on transit can vary from say 16,000 to 12.5 million, depending on at what rate data is being sent. And these are the drawbacks, you can say, because we shall see the techniques that we have developed for local area networks, the medium access control techniques, cannot be used because of this. However, this feature is very important. All the stations receive its own signal. That is a very advantageous thing. We shall make use of these two properties in devising the medium access control techniques. Now, another point that you should look is the traffic pattern. A communication satellite is used for various purposes, for the communication of telephone signals, TV signals, data. So all the different kinds of traffic are sent, and they can be broadly divided into two types. One is, as you know, burst-T. The data is sent in bursts, or it can be stream traffic. Continuously it is being sent, as it being done in case of telephone communication. So there are two possibilities, and your traffic pattern can be a mixture of these two. Now, based on these characteristics, let us see which technique can be used. Can we use round robin technique? In round robin technique, there are two basic approaches we have seen. One is called polling. If we use polling technique, just to poll one station, you have to spend about 1/4 of a second just to send the signal, and then receive an acknowledgement, another 1/4 of a second. So polling is not suitable because lots of time will be wasted just for polling purposes. Similarly, token passing cannot be used also, because the signal, the packets, the token that will be transmitted, just for sending tokens you have to spend again 1/4 of a second. As a consequence, the round robin techniques are not suitable. Can we use CSMA, carrier sense multiple access type of approaches? The answer is also no. The reason for that, the CSMA based approach is based on monitoring the channel to see whether carrier is present or not. But in satellite, what you are receiving now happened about 1/4 of a second earlier because of long delay. In other words, the value of A, that the ratio of the propagation time by transmission time, is quite high. As a consequence, the CSMA based approaches cannot be used. Then what is the possible candidate? Possible candidates are Aloha and slotted Aloha, which can be used in satellite based communication. But if we use just Aloha or slotted Aloha, as we have seen, the throughput is not very high. If you use Aloha, the throughput is about 18%. On the other hand, while using slotted Aloha, the throughput cannot exceed 37%, that we have already seen. So to improve the throughput, we have to use area network. That means man standard. In addition to this, that can be done by using reservation technique. That can be done by using reservation technique. Reservation based. We have to use reservation based schemes. And these reservation based schemes can be broadly divided into two types. They can be distributed or centralized. We can devise a scheme where all the ground station will take part, will do the medium access control in a collective manner. Another possibility is that there will be one ground station which will act as master to impose the, or rather to perform the control, medium access control. So both the techniques can be used. One important feature is, in all cases, what is being done, a fixed frame length is used. There is a frame length, a frame, it is sent in terms of frames. So a fixed frame length is used. And this frame is divided into a number of slots. It is divided into a number of slots. Let there be m slots. Let there be m slots in each frame. Then this frame is repeated after the one after the other. So this is frame number 1, this is frame number m, and then frame number 1 will come, and so on. So all these schemes are based on this concept of frame. Now let us assume there are k stations under one transponder, and the communication is taking place using those transponders. Let us first of all consider the distributed schemes. The first scheme is known as R aloha. R stands for reservation. So we shall make use of reservation along with slotted aloha or aloha to improve the throughput. Let's see how it can be done. This R aloha is based on the assumption that K, which is the number of stations, is much greater than the number of slots. Then what is being done? Implicit reservation is done. Let's assume this is the frame. I am showing only one frame. We have got a number of slots. Reservation is done in an implicit manner. How? All the stations are receiving the signals present in each of these frames, in each of these slots. At a particular instant, if a station finds that a particular slot is empty, no data has been sent by any station, it tried to reserve that particular slot by sending data in that particular slot. So when the next frame will come, it will see its own data, and then it can find out that a particular slot, whether there is collision or no collision. If another station has tried to send using the same, during the same slot time, then there will be collision. In case of collision, obviously in the next frame time, this station will not send. So by using slotted aloha, reservation is done for next frame. And in this case, it is necessary that the frame length has to be greater than the bit length. Why this is necessary? This is necessary because after monitoring the present frame, the stations are deciding what it will do for the next frame, whether a collision occurred or a successful reservation or successful transmission was possible, and depending on that, decision is taken. So stations must know what happened in the most recent frame, and accordingly decision is taken for the next frame. Now, in this particular case, whenever you have got long messages, so for long messages, in this case, each slot more or less gets reserved for different stations, which is equivalent to TDMA. So it works like time division multiple access, TDMA, because you are sending in different time slots for different stations. On the other hand, if the traffic is burst in nature, then it is behaving just like, it works like S aloha. In slotted aloha, we have seen that different slots are used by different stations, one after the other. No slot is booked by any station. So whenever the traffic is burst in nature, it works like a S aloha. On the other hand, for long messages having a large number of packets, it acts like a TDMA, time division multiple access. And the improvement, what can happen, say, unless one station finds that a slot is empty, it will not send in the next slot. As a result, some of these slots will go empty. This can be avoided by using a technique or by incorporating what is called end of flag. You can incorporate an end of flag in the packets. So when a station sends the last packet, the end of packet is incorporated in the frame. And by looking at that, other stations will know that this is the last packet of that particular station. Accordingly, in the next time frame, another station can try to reserve it by using again S aloha. So this is how this reservation aloha based scheme works. It was proposed by Crowther and his associates. Subsequently, other techniques have been proposed. Let us consider the other approaches. The binder scheme. In binder scheme, it is assumed that K is less than equal to m. What does it mean? You have more number of slots than the number of stations. That means when the number of stations is less than the number of slots in the frame, then this binder schemes can be used. How it works, let us see. This is the frame, and you have got a number of slots in the frame. What is being done? In binder scheme, one slot is assigned to one station explicitly. Let's assume this is assigned to station 1, this is assigned to station 2, 3, 4, 5 and 6. Let's assume there are 6 such stations. So 6 stations are assigned with one slot for each of them. What about the remaining slots? These excess slots can be reserved by these stations if they have data, so by using slotted aloha. So excess slots can be reserved by S aloha, slotted aloha scheme, which you have already discussed. Now here also it is necessary that frame length is greater than the bit length. For the same reason I have explained for the earlier scheme, the reservation aloha. Here we find that we are using a combination. We are performing explicit reservation for one slot for each of the station, and the excess slots are being used. Excess slots are booked or reserved by using implicit technique or in an implicit manner. And this is how it works. Now suppose station 1 has no data to send, so this slot will go empty. So whenever a station has no data to send, the slot explicitly reserved for it will go empty. What the other station can do, they are constantly monitoring, because all the slots are being monitored by all the stations. It is a broadcast communication by using that downlink frequency. What the other station will try, in the next frame it will try to reserve by sending data in the slot number 1, since it was empty. So even those slots which are reserved for the stations can be used by other stations whenever those slots go empty. However, when that particular station 1 wants to again get back, it simply sends a frame in that slot. Possibly the first frame will suffer collision, but subsequently this station which was using that particular slot will come to know about it, so subsequently it will not send. So this is how in this binder scheme the different slots can be used, a particular station can use it, can reclaim it whenever necessary, can release it and reclaim it whenever necessary, whenever it has got data or no data. And it has been found that this is superior to reservation aloha for stream dominated traffic. It is better than R aloha for stream dominated traffic because of this explicit reservation. So it is making use of this explicit reservation, and then it is also using the implicit reservation in the excess slots whenever there is stream data for some of the stations. However, for large K, there is large average delay. Another point, another scheme which was introduced by Winder, the length of the queue in each of the station can also be communicated as part of the frame, and which is being monitored by different stations. And by looking at the queue of different station, other stations. In fact, this lecture was supposed to be for local area networks sending data. So this is how a global queue is maintained. In this, each station can maintain a global queue by receiving information from the frames sent by different stations. Now let us consider another scheme which is also distributed, which is known as Roberts schemes. Roberts scheme is based on explicit reservation. How it works? Again, let us draw the frame having a number of slots. Here, the first slot is divided into a number of mini slots. So this is your first slot is reservation mini slots. What is being done in these reservation mini slots by using S aloha, different stations tries to send many packets and perform reservation, and a common queue is maintained. And by looking at that common queue in this reservation many slots, the remaining part of the frame is booked, and these are the reservation slots. Which are booked, reserved using this mini slot, and then used subsequently in the other slots. So each station comes to know about current global queue, and after the end of the current global queue, each station will try to send data. Now, whenever you have lengthy data, of course, there is a restriction. Let R is the maximum number of slots that can be reserved. So, based on this, it has been found that utilization is equal to R by R plus 1. This restriction is necessary because if a station has a long message to send, it may reserve the entire slots for a long duration. That is not desirable. So for the purpose of fairness, it is necessary to impose this restriction. That is the reason why for lengthy stream of data, for lengthy stream, frequent contention is required. So you have to book separately, as you do in your railway reservation. Each person is not allowed to book reserved for more than 3 or 4 persons. The same thing is applied here. An analysis shows that this is a significant improvement over S aloha. Here, by using S aloha, you are performing reservation in the mini slots, then you are sending data in the mini slots, and by that you are able to improve the throughput significantly. So after discussing various decentralized schemes, let us now consider the centralized schemes. In centralized schemes, what is being done? One of the station takes the responsibility for reservation. As a result, it imposes less burden on the stations, and also it is not vulnerable to loss of synchronization. In decentralized schemes, it is necessary to maintain synchronization among all the stations so that the scheme works properly. However, there is some delay because of this centralized booking, and this extra delay is acceptable for even to stream traffic. Let us consider the first scheme based on this centralized reservation, which is known as fixed priority oriented demand assignment, or in short FPODA. This was devised in United States for 6 local area networks for communication through satellites. So 6 local area networks were communicating through a satellite, and for them it was designed. What was being done? Here there are 6 mini slots present downstream. So this is how the communication will be done. And out of these 53 byte cells, only 44 byte signal can be sent by different stations, and the remaining part of the frame is used for sending data by different stations. Now, each local area network can send at the rate of 1 megabits per second, and the frame length is 130 millisecond. And one of the ground stations monitors these 6 mini slots and does the reservation for the remaining stations. And this is how the communication goes on. and this has found to be effective for fixed and small number of stations. It cannot work whenever the number of stations is large. Fortunately, in this particular case, it was designed for 6 LANs for communication through satellite. Let us consider another centralized scheme which is known as packet demand assignment multiple access. Or PDAMA. In this case, the frame is divided into 4 parts. There is a leader control slot, and after that there is a guard slot of 280 millisecond. This guard slot is used by different stations for the purpose of ranging and evaluation. On the other hand, this leader control slot is used by the ground one of the master this controller to send reservation information through it. And the reservation can be done in the third slot of the frame, which are mini slots, reservation mini slots. And in this reservation mini slots, the requests can be made by different stations by using, again, S-Aloha. And accordingly, the controller will pass on the acknowledgement and reservation information in this leader control slot. And this slot will be used for ranging by different ground stations. And in the remaining, the fourth subframe you can say, you can send the variable length data. The data can be of variable length by different stations. And this was developed by NASA for mobile satellite system. Nowadays, another approach is becoming popular. The satellite is becoming more and more powerful. It is possible to put even a computer in the satellite. The satellite can also act as a master. In the earlier discussion so far, we assumed that the satellite acts like a bent pipe. It is passive. It can receive a signal by using uplink frequency, then retransmit it by using downlink frequency, which is broadcasted. But you can use the satellite as a controller, and which will do the reservation for different stations. And based on this, satellite oriented control has also emerged, where different reservations can be done by ground stations, and in the satellite there will be a controller which will do the reservation, and accordingly in different slots the communication will be performed. So let me conclude this lecture by summarizing what we have discussed so far. We have discussed 3 basic approaches for medium access control, which are essentially asynchronous, round robin, and contention based. Under round robin there is polling and token passing, which are suitable for stream traffic and used in local area networks. The contention based schemes which are used in also local area networks, are suitable for BAST traffic, which are Aloha, CSMA and CSMA-CD. And today, in this lecture, we have considered the reservation-based schemes, both centralized and decentralized, which are used in satellite-based wide area networks. Thank you.